Okay, so today is the 10th of October 2019, and this is tutorial session number 5 for investment and portfolio analysis. Um, okay, just let me try and join from the other PC as well. Okay, now, so first of all, I really do appreciate you guys, your understanding. We are living in extraordinary times, and you are going through something that I have never gone through, and maybe not even my parents. So I want to thank you quite sincerely for that. Let me just run a few things by you by way of housekeeping. Um, so tomorrow there will actually be two teams presenting. Oh, while we're on this page, this file is already online in Blackboard. Okay, I've now just admitted myself. Second screen. So now you see there is two of me. Buy one, get one free. What was I saying? Yeah, so this file is already online in Blackboard, and on this page here you will see I have provided a link to the assignment answers. It's read only, but you can go in there and read it, and you should only need to read it, I think. And every week, um, when we have gone through solutions for new assignments, that file will actually grow, and there will be new pages um, attached to it. Okay, so this is where you can look for that file. As soon as you click on this link, you should be able to go directly to the file, and you see it's weekly assignment answers, so it's all there. Now, that's the first thing, and the other thing I want to mention is that so this is a calendar, and today we are here, so we are basically halfway through. We're supposed to meet 10 times for tutorials and 11 times for lectures, and so we are kind of meeting tonight, up in the information superhighway. Next week, actually, there is no tutorial. Maybe for that's just as well, because we don't know what's going to happen next week. But I was not planning to have a tutorial next week because I will not be in Hong Kong, actually. So the next time we meet after that will be 24th. Now, this session normally is supposed to run, as you know, on Thursday evening, which we are doing now, but we're not together, from 6:30 to 8. So if you read that uh, email yesterday from the department, it looks like that we're not going to meet anymore in the evening for the rest of this term. So I have to think about what to do with this tutorial. So quite likely, I have to reschedule. I have to find a time on a weekday afternoon and then relocate some of you there. Now, currently there was one session to start with, which was this one, which is every Wednesday afternoon at 2:30. There is actually another one, as you know. I sent out an email a couple of weeks ago in CKB 706B. I think I will keep running that because that's 6 o'clock and it's still early enough. I know we're all going to go to bed quite early from now on. But this one, I think I will keep it. And I think I will probably try to find time to set up another one in the morning or afternoon, Monday to Friday, in order to accommodate these sessions. That's what I have in mind right now. Okay, is everyone okay with that? Is everyone still there? Okay, that's good. Please let me know if you have any questions. Okay, now in terms of housekeeping, no, there's no quiz. Okay, forget about that. In fact, okay, a piece of good news for you. There will not be any more quizzes in the lecture from now on. As far as I know, I think Professor Fong is pretty much done. So he's only quizzed you 2 times, and he gave me instructions to give you a short quiz in the tutorial, maybe another 2 times. And I'll give you plenty of warning, so do not get stressed out, okay? And I will give you plenty of warning and let you know how to prepare and so on. And what we will do is, so altogether you're going to be taking, you will take 4 quizzes, and we will take maybe the best 3 out of 4. So if you were absent for some reason for one of them, or if you think you completely messed it up, which I don't think is possible, then don't worry about that, because we are not going to count the one your worst one. Okay. What else? Yeah, and you should know by now that last Friday, at the end of last Friday, Friday afternoon Hong Kong time, if you are doing a project on a Hong Kong stock, or Saturday morning Hong Kong time, or Friday night New York time, you should actually find out what was the closing price of your stock and put it into a form. So these 2 events have already happened. I want to thank you for all your submission. Tomorrow you can print out hard copies. I think 1 copy is enough. I don't need hard copies. I'm going to try and read it online, just to be kind to the trees. But tomorrow, please bring your hard copy. You don't need to bring your PowerPoint to present, because I will download everything and then help you load it up to the computer. Okay. Now, you must be wondering, so where do you put your investment entry price? Okay, so I have created another form. Yes, I have. And okay, so tomorrow the teams that are presenting are going to be Master of DDL. I know what that means now. And Psycho Satoshi. Now, we have to determine today who is going to present on October 18, and that's kind of how it will work. So every week, on a rolling basis, we will do a lucky draw. But first of all, let me just take you to this. Now, if you click on this one, it will take you to a form that you are supposed to fill in And I can see that it has been filled in by absolutely nobody. Well, that's not good, guys. So you put in your at least you can fill in column D, okay, and I would check it. So if every group does a little bit, it means that I don't have to do something 10 times, okay, and I would really appreciate that. Is everyone okay with that? Hello? Okay, wonderful. I just sometimes if I talk for too long and I don't get any response, I fear either you left or you got disconnected or you fell asleep or something. Okay, now, so I tell you what. So I see that the first person that is there is Zhang Yuqing and then Zhang Tianfang. Okay, Yuqing, how about this? Can you just give me a number between 3 and 10? Any number? Huh? 7. Lucky number 7. All right. Hold on. Some paper. And so 7. How about Tianfang? Can you hear me? Good evening. How are you? Can you pick a number? Can you pick a number between 3 and 10? Any number, but not 7. 3. Okay. Now, I uh, so what I'm going to do, I actually have a spreadsheet. Um, we are not going to do the presentations in sequence, and I'll tell you why we're not. Because it's probably, if we do it in sequence, and so, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then group 9 and group 10 will know that they are going to be doing it at the end. I think that might be a little bit unfair for them, for the other teams, because you would have a chance then to uh, observe how others are doing. So we want to just keep it random, which means that everyone will get around 7 to 10 days to prepare. And just for your information, Psycho Satoshi and Master of DGL, we actually did a lucky draw. We did do a lucky draw last week, but it was on Wednesday in WMY. So that might be why you didn't see that. But I did that in front of the other class, so you can go and ask them. Now, so these are the teams that haven't uh, that have yet to present, and just now uh, Tianfang and who's the other person? Forgot now. Yeah, thank you. So they picked numbers 3 and 7. Now I actually jumbled up the sequence. So number 3 is fortune teller. So you guys are the lucky ones. Oops, no, hold on. 18th of October. 18th of October. You guys are the lucky ones, and together with Alpha Chose Us. What a cool name. Okay, so these two teams will be presenting next week. Is that okay with you? Everyone is okay with that? Sorry? You are in group 3. Why is that? That's You don't have to say sorry. First of all, it's random. Who's me? Look, Alice, you don't have to apologize for anybody or anything. First of all, I asked you to pick a number. Secondly, you have no clue what that was for. And number three, it's all random. And number four, I think you're actually helping them. So you know they get to present. We do make some adjustments for the teams who are presenting first because they do not have the luxury of actually observing teams who come on later. Okay, so I think it's only fair that we try to give a little bit of allowance. Okay, all right. So that's sorted out in front of everyone. Now, what I want to do and please fill in those prices as I said. Okay, I need your help on that. What I want to do today actually is to go back a bit to the tutorial file of last week, and I want to just run through a number of issues with you. And I know that we got up to talking about Schiller, and just a very quick reminder, because some of you were still asking me about multi-period models. I want to start by looking at that. This is a question that is not often asked, but when someone asks that question, frequently some people cannot answer it. Now, what is the difference between so-called single-period models and multi-period models? The only difference is, by definition, any model that will require you to make some changes to certain input parameters from time to time, you can classify that as a multi-period model. The best example is probably that multi-stage Walmart case that we went through, because there were like three stages. There was like the growth phase, and then the consolidation phase, and then the maturity phase. And in each of these phases, you had to make different assumptions about the growth rate and so on. The cap M, for example, and here I have an equation for the cap M, is an example of what I would call a single period model, because according to the cap M, which is not a law in physics, by the way, it is just a model that some people think is a correct characterization of stock returns. Then the return should be equal to the risk-free rate plus beta times the market premium. Now, this actually does not change over time, and you're supposed to price that, and it goes on forever. So that would be an example of a single period model. If you were to use the dividend discount model, the DDM, but you use the most basic formula, which is price is equal to dividend divided by interest rate minus the growth. If you were to do that and you do nothing else, I guess you could argue that this is a case of is another example of a single period model. Okay, so I just thought I'll clarify that. And as soon as you start making adjustments, and some adjustments can be very complex, the professional researchers, then it is not a single period model anymore. Is everyone okay with that? Thank you. Then let me now have a look. Now, I want to talk to you about this this picture, which is actually sourced from one of the slides in Professor Fong's lecture notes, and it is well, it is part of what people call prospect theory, in trying to explain the relationship between utility and wealth. Okay, now utility for me is it's a very abstract kind of concept. It's not exactly happiness. It is kind of usefulness, I guess. So you wouldn't equate, having a lot of wealth to a rise in happiness. Although for some people that might be the case. Um, I know we all prefer more utility than less, but it's kind of hard to measure, and I would say even hard to put your finger on. But one thing is clear: more utility is always preferred to less. So that we know. So what you have here is a graph, which is the change in wealth on the x-axis, and your change in utility on the y-axis. And there was a time when I only see like this part on the top right hand corner, and you might think, well, yeah, what is the big deal? It's just a blue line in a graph, and a curve that goes up like this and goes down like that. I think it actually explains quite a lot about human nature, and let me I can make a number of points at various spots in the graph. Now, spot number one is this one. So when you are out here, you see that the line is kind of rising, but gradually the slope is decreasing, and then it just almost becomes flat, but not quite. Now, that is telling you that when you have made your first $5 million, you are a lot more excited in terms of change in utility than when you have already made $20 million and you just made another five, and then the utility practically doesn't change. And I think that's very true. In economics, there is even there's a term for it. What is it? Marginal diminishing return. Okay, which is another way of saying when you have a lot of something, you are no longer so excited by it anymore. You don't get the same thrill. Whereas if you are here, that's different. Now, let's say that's point number one. Point number two. I think all of this actually has important implications for people who want to become portfolio managers and traders. So it's not just purely academic. You can't trade or invest in the market unless you understand human nature, and this graph explains that. I can think of at least four different aspects, and I'm trying to point them out to you one by one. So number two. So let's say someone has $5 in the pocket. So when you have that money, so this will be your current utility, and if you ask that person whether they are happy to take a gamble where they have a chance of winning 5, which would take your wealth up to 10, or losing 5, which means you end up back at 0. Now, a lot of people would be quite reluctant to do that, and that is the name for that technically is risk aversion. But how do you actually explain risk aversion? Well, you can explain it because of the convexity of this curve. Because if you were to draw a straight line between the two dots, then if you currently have $5 and you have a 50% chance of making $1 and 50% chance of actually losing $1. So if you take that gamble, your expectation is actually equal to 0. So your expected wealth would still be 5 if you currently have 5 in your pocket. But guess what? In this case, your utility, your expected utility will actually drop by this amount if you were to take the gamble. And this, it quite neatly explains why generally people are risk averse. Now, that's point number 2. Point number 3 is like the mirror image. Oops, sorry. The mirror image of point number 1, which is when you are here and you have lost $25 million, let's say you lose another $5 million. So your curve is going to be like this. So now you're here. You can see that to go from minus 25 to minus 30, there are hardly any changes in your utility level, which is another way of saying when you have lost so much money, yeah, well, who cares? Another $5 million. I'm already ruined. So, and then if you gamble, maybe it'll take you back up to 20. But if you were to lose another 5, you don't feel much. You already feel pretty bad. You do, but you don't feel worse. Okay, that's the point. Now, point number 4 is the one that scares me the most, because I have seen this kind of behavior so many times, and that is when you are losing a little bit of money, so you've just lost 5. What happens if you take a gamble in the hope of trying to recover the 5 that you lost so that you become break even again? Now, if you just do the same as before, you draw a straight line between 0 and this point, this is now your expected utility. In fact, your expected utility goes up. It is still negative because you are below the x-axis, but it is going up. Whereas here, it is coming down. That's another way of saying if someone has a loss, someone has incurred a loss, at the initial stage, they are actually quite inclined to take a random gamble in order to try and recover it. And I'm sure you know someone around you who has exhibited that kind of behavior, either if not in a stock market, then perhaps even in a casino. So I thought that's worth pointing out, just a little graph like this. Okay. Is everyone okay with that? You can either just say something or you can type a little message. Okay, thank you. All right, now one more thing I want to mention about correlation, and I know that this is an issue that some people find confusing. Okay, so I want to try and clarify. Let's say that you are running. So there are there's a data set called Y1, and it has a lot of numbers, and a data set called X1, and it has a lot of numbers, and there is another data set, Y2 and X2. They got nothing to do with each other, okay? So Y1, Y2 might be the sale of ice cream when the weather is hot or something like that. So sorry, Y1, X1. Y2, X2 is y2x2 can be, the number of times people go to the cinema, during the weekend or whatever. Okay, so they got nothing to do with each other. And let's say you are now, you try to investigate into whether there is a relationship between these two time series. So what you do typically in econometrics is that you try to run regression, and you put the dependent variable here, and then you claim that y1 has a relationship with x1, and there is also an intercept, and you try to do the same for an entirely different experiment. So this would be m1, b1, m2, x2, and b2. Now let's just say that in the case of x1 and y1, the pattern of the variables kind of look like this. So it's all over the place. And when you run a regression, it would look something like this. And if I was to put some values to it, so y1 might be equal to, let's say, 0.85 times x1 plus b. It doesn't matter what b is. Okay, so that is one data set. Now on the other side, maybe this is y2, and as I said, y2 x2 has nothing to do with what's happening over here. Okay, and here it looks like this. They are perfectly in line, or almost perfectly. And when you run a regression, you find that y1 is equal to, let's say, 0.2 x1, sorry, 2 x2 plus b2. And then, so, all right, let me ask you this. So the one on the left-hand side, so there will be a correlation between the two. And then on the right-hand side also, which one will have a higher correlation, row 1 or row 2? I know you cannot judge because I haven't given you any numbers. I haven't given you Excel, but just by looking at the graph like this, which one do you think has a higher correlation? The one on the left or the one on the right? The one on the right, yeah, because they all line up perfectly. Now, here's the thing. So the correlation here will be very, very close to, is practically what I on purpose, I'm drawing it like this. Whereas the correlation here, because they're all over the place, correlation at best will be, let's say, 0.6. It doesn't matter. Now, my point is this. I have seen people make a mistake by saying, oh, y1 and y and x1 are very highly correlated. They make a mistake correlated. They make a mistake of confusing the coefficient here with the correlation. Now, when you say something is well correlated, you are looking actually at this parameter, or the R square, which is just a square of this in a one variable case. You are not looking at this regression coefficient, and then you don't do that and then come to the conclusion that, oh, they're not really correlated. This tells you about the sensitivity of how y can move when x is moving. But if you want to know something about the quality of the relationship, the quality is actually represented by the correlation coefficient. Is that okay with everyone? Do you know what I'm saying? I know that most of you understand this, but maybe some of you don't. So I wanted to just highlight that because there are some, correlation exercises coming up, and unless you are completely clear on this, I have a concern that uh, many people will end up getting confused. Is everyone okay? Hmm. Thank you. Now, for example, just to press that point a little further, uh, so you can have, uh, let's say, the return of a certain stock, and you look, so that's a time series. Every day there's a number of daily return, and you also look at the uh, I think the notation is using the capital R. Now this is the market premium, sometimes it's called. Okay, you might have seen Professor Fong using this notation. If not, he would do so very soon. So this is the excess market excess return over the risk-free rate. Now, so let's say you also have a series of numbers, and then you start running a regression of one versus the other, and you end up with some kind of funny looking equation. Um, so, okay, I'll say this is B, okay, plus, what notation was I using? Uh, M. I'm just trying to be consistent with my notation here, okay. So of course you can run that kind of regression, and it's very easy to do so, and you might find that Ri would be very close to uh, the expected return of the stock, and B would be very close to the risk-free rate, and M would be very close to the beta that you are expecting from that stock multiplied by RM. Now, here is the $1,000,000 question. I have seen students say, oh, look, this is the correlation between the uh, the stock return and the market excess return. No, it isn't. This cannot be the correlation for a very simple reason. The correlation parameter can only be between 0 and 1. The beta of a stock can be anything. Well, not anything, but it can be positive, it can be negative, it can be bigger than 1, it can be less than -1, at least in theory, okay? So there's no way you can say that this is the correlation. It is not, okay? So don't make that mistake, please. Everyone is okay? Uh, all right, now let me then, I want to actually just take a look at some of the questions in Bodhi chapter 4, and I thank you for the homework, by the way. Uh, the starting from this week, when you start doing homework for chapter 6 and 7 and so on, so there will now be a convergence between your homework and some of the lecture material. So I hope you will be able to spend some time, and I'll certainly provide the answers to you later on, and if we have time, we'll go through some of them selectively. Okay, but here, question. This question is actually quite simple. Question number 13 in chapter 4. Now, the solutions will be in that file soon, but I actually want to have a look at this one in chapter 5. And I was quite surprised. I got asked all sorts of questions, including questions that I was not expecting. Um, so here is a question asking you to derive the probability distribution um, of the 1-year HPR on a 30-year US Treasury bond with an 8% coupon if it is currently selling at par, and the probability distribution of its yield to maturity 1 year from now is as follows. Now, my first question to you, can someone tell me uh, what is the meaning of HPR? Does anyone know? Who's that? Okay, who was talking just now? Was that Tian Fang? Okay, who was that? All right, look, you know you can earn participation points even when you're online like this. So I'm just trying to make a record of who has spoken. Okay. It is holding period return, and if you ever want to become a fund manager, this is one thing that you must know, um, which is, in fact, you guys are about to calculate the holding period return of the stock that you are researching on, which would include all the capital gains and any potential dividend income. Now, the first thing, so there are a number of funny things going on here. So first of all, there's a bond, and it has an 8% coupon, and it is currently selling at par. You know how if you want to know the price of a bond, it is really just a function of three things. So first of all is the time, second is the coupon. What's the last one? Uh, Not quite. The face value will tell you exactly what you should pay. So for example, if a bond was priced at 99 and the face value you buy it and you buy $1 million, then you will end up paying 990,000. There is another parameter. Very good. Who was that? Thank you. That was Jiswan, right? Okay. Good evening. How are you? I'm well. I even managed to have a little bit of dinner tonight before I came online. Um, you need the discount rate or the yield for this. Okay. So the question is, when you have a bond and it is paying an 8% coupon and it is selling at par, what does that tell you about the yield? What would the yield be if the bond has an 8% coupon and it's actually selling at par? Does anyone know? It is just 8%. So now I am aware that in our course, maybe there's not all of you will have exposure to fixed income, which for me is very, very important. So here and there, I try to at least share these concepts with you. And concepts are the concept here is for bond price, and I guess most of you know this. Um, uh, with respect to the relationship between coupon and yield, then, like I just said, when the coupon and the yield are the same, then the bond will be at par. But when the coupon is less than the yield, the bond price will actually be at a discount. In other words, less than $100, 90, 99, 98, or whatever. Whereas if it was the other way around, if the coupon is bigger than the yield, then it'll be priced at a premium, which is to say greater than $100. It's what we call above par. Okay, so this is the first thing I want to point out. The second thing is, so you have these probabilities. So in the event of a boom economy, then which has a 20% chance, the yield of treasuries will go up to 11%. So from 8%, the yield goes up to 11. And if it's normal growth, then the yield is essentially unchanged. But you will only know it's unchanged if you knew that the starting yield is 8%, which requires you to know that when a bond is priced at par, then the coupon and the yield are the same. Okay, and then in a recession, it is usually the case that in recessionary times, which has a 30% chance, interest rates generally go down. Okay. Have you guys ever heard of a term called stagflation? Now, this, I don't think it ever was a proper word in the English dictionary, but this is a term that I think people came up with around 30, 40 years ago when we had a period of very, very poor growth, but at the same time, inflation was very high. And that's what they call stagflation. Okay. There are people who think that if the trade war between China and the United States, if it keeps going on the way it is going now, and if it gets any worse, we may well have that problem. And I am wondering, you might want to just think about that. You don't have to agree with me. The rationale is, so first of all, it's not really good for these two countries to be engaged in a trade war. So that would probably result in poor economic growth. But at the same time, because China sells a lot of goods to the United States at very competitive prices, if that was to disappear, then it potentially can contribute to inflation. Okay, something like that. You might want to just look that up. So anyway, now back to so we are asked to derive the probability distributions, and then you just assume that there's only one coupon paid at the end of every year. This is not really so relevant. Now, this is the answer, and it is not much of a distribution. If you insist on looking for a distribution, then it would look something like this. So you have you don't have a beautiful bell curve, but you have just a distribution with 3 columns, and on the x-axis are the returns. The base case is 8% of normal growth, and in boom time, which has a 20% probability. So this, and then the yield goes up to 11%. The price of the bond drops to $74. So you actually will suffer a capital gain, well, capital loss of around $26, but because you get paid a coupon, so that helps a little bit, and your holding period return in the end is around minus 18%. So this is the minus 18% here, and this, I guess this box here would have an area of 20%, whereas this box here would have an area of 50%, and this area would have this box would have an area of 30%. Everyone is okay with that? Now, I was asked, yeah, how do you say that in 普通话？债账 or 债章, yeah. You know what I mean. I'm not the person to consult on 普通话. We did have that 40 years ago, but that had a lot to do with the oil crisis at the time. So oil prices, energy prices were very high, so inflation was high, and that actually pushed global economies into a recession. What was I saying? Yeah. Now, you might wonder where these prices actually come from. So the one in the middle is easy. So this is just at par. So when one important point to remember is that 1 year from now, you are going to be pricing a 29-year bond. So fixed income is challenging that way. The time changes. A 30-year bond is only ever a 30-year bond, strictly speaking, on the first day when it arrives in the market. The day after, it is a 29-year, 364-day bond, and so on. Now, so how do you price this? So remember these numbers, $74.05 and $112.28. Now, on the page before, I tried to provide a little calculator. If you click on that, it takes you to a page. It's a very, very simple calculator, just to show you that those prices are not bullshit. Okay, so I'm going to price out of 100, and coupon is 8%, and then if the market rate, that's just another way of saying the yield, is 11, and years to maturity is 29, and I'm going to price them annually, although the price wouldn't change all that much. And then I'm going to hit enter. And the price you should get is $74.05. And then if you put the yield equals to 7, hit enter again, the price is now $112.28. Is that what we had in the answer? $112.28. Yeah, this one here. Okay, so if you are not familiar with fixed income, I would suggest, ladies and gentlemen, this really is the minimum that you must know. You could consider just coming over to this website here, and I already gave you the link, and down there they actually explain how they do that. And they even gave the formula for bond price, the very, very simple bond pricing formula. So this one, okay, so I don't really need to repeat it here, but that's what they were using to price these cash flows. So make sure you're comfortable with that, and if not, please do let me know. Okay? Thank you. Everyone still awake? Now, I want to have a look. You know, I tell you, it is a challenge to talk like this in front of a screen. I'm the only one in the room here, and it feels very, very strange. Um, Now, this question, I want to just go through it. It is quite meaningful because it allows me to share with you, I think, a fairly key market insight to asset price behavior. And I might have just very quickly touched upon that when we were still having those classes in the pre-term finance in August. I mentioned that asset returns are basically not normally distributed. This question is a little bit related to that, and I'll explain in a moment what I mean by that. Now, so what they want you to do actually is to dig up this data set, which has annual holding period returns for different asset classes, well, specifically stocks and bonds. And you are asked to calculate the mean, standard deviation, skewness, and kurtosis of these numbers using either 30 years of data, but I think they also provided additionally close to 100 years of return data. Now, this is a good time to talk a little bit about the various attributes of the normal distribution. So normal distribution is, it sort of looks like the classic, bell shape, but it is actually a lot more complicated than that, and there are specific requirements, and we'll have a look at that. Now, when you are trying to analyze a data set, it can be anything. Okay, let's say you look at all the students in the university and you want to look at their weight or their height. There is normally, some kind of average value, and then there are people who are extremely tall and some of them are a little bit short. So end up you have some kind of a bell curve. But that doesn't tell you a lot unless you actually look deeper into it. And anybody can throw in a bunch of numbers into Excel, just a data set with a whole load of numbers, whole load of observations, and then calculate using the average function and the standard deviation function. You'll get some value coming out of that, but that may not be meaningful. Now, to give you an extreme case, if you look at these two distributions on the right-hand side, there's one in red, which looks a little bit like a bell curve. So it has some chance of being a normal distribution, but the green one has absolutely no hope. It's clearly not normally distributed. In fact, it's kind of, it's got two peaks. It's bimodal. There's a peak here and there's a peak here. So definitely the green one is not a normal distribution, but these two distributions can end up having the same mean and the same standard deviation. Okay, so that means if you have a bunch of numbers, and when you are working on big data, it could be a million numbers, and then you find a mean, you find the sigma. Sigma is another word for standard deviation. Don't be so happy yet, so because you don't know what you have. Just looking at it like this, okay, it could be it can be any kind of funny shape. So what do we do now? The mean of any sample data set is commonly referred to as the first moment, and the variance, maybe not the sigma, the variance is sometimes called it's called the second moment. I will now take you to what's called a third moment, which is when we test for skewness. Okay, skewness is just another term for something that is not symmetric. So you can see from the bottom diagrams that when something is positively skewed, so it looks like this, and when it's negatively skewed, that means there are far more negative values. There are much more negative values to the left side of the mode. This is called the mode. Okay, the mode. Mode is this is the mode. Okay, mode is just a word for the most popular observation, or the one with the maximum number of incidents. So when it's negatively skewed, there are a lot more values to the left-hand side of it. If something is skewed, if you test for a data set and the skewness parameter is not equal to 0, or it's significantly different from 0, then you will come to the conclusion that there is some skewness, which is to say they're not symmetric. You cannot fold them up. So forget about normal distribution. When they're not even symmetric, how can they be normal? Okay, and the formula is the one. Scribbling. The formula is this one here on the bottom right-hand corner. The reason it's called a third moment. You see, there's a cube, the power of 3 here, whereas variance, it only has it's up to the power of 2. So this is how you test for skewness. Now, suppose you find a distribution, and so you have a mean, you have a standard deviation, and you test for skewness, and there is no skewness. Can you then come to the conclusion that this is a normal distribution? Do you think you can do that? So no skewness, and a pretty normal looking mean, a pretty normal looking standard deviation. Skewness is 0. This is actually not enough, because you have to test for a fourth parameter known as kurtosis. Okay, and now this is to do with what we call fat tails and higher peaks, and you hear this in finance, and certainly in the derivative world, and in option pricing. All the time you hear about this. So what is it? Let me show you some funny graphs. Okay, now here I have a whole load of distributions, and they share a number of characteristics. So first of all, the means are the same. I don't know if the standard deviations are the same, but they all have 0 skewness. So they're all symmetric along this line. Okay, but now we are testing, as I said, for what we call kurtosis. Now, only one of them actually is, strictly speaking, a normal distribution, the black one. Okay, it has a kurtosis reading of 0. Yeah. Now D, which is this distribution here, is rather extreme. It has a kurtosis reading of 3, and even S, which is this one here, or the yellow one, L, so D, S and L. These are all not normal distributions. And if I was to draw it with a little bit of exaggeration, then what it means is if this is a normal distribution, so the black one is a normal distribution, something that has what we call positive kurtosis, kurtosis, would look something like this. Okay, I'll write it in blue. So positive kurtosis. Now, to start with, they will have fatter tails, and then in the middle they're a bit skinny, and then when you get to the top, they rise a bit more, and then on the other side, they also have a fatter tail. Now, this is a distribution, I'll tell you right now, that relative to the normal one, this one will have positive kurtosis. And the formula that you would use to calculate that is this one on the bottom right-hand corner, which is why, ladies and gentlemen, it is sometimes called the fourth moment. You see, it's up to the power of 4. 1, 2, 3, 4. One thing to keep in mind, though, which is this is the formula for what we call excess kurtosis. Notice that there is a hard-coded number 3 at the end. Some people, sometimes, they quote the kurtosis formula this way. Okay, now, in our case, for this graph, for example, they are using the entire formula, including the 3. So that is why if this part is equal to 3, only this part, then your excess kurtosis will be 0, which is what we have here, in here, okay? Now, so you don't have to argue is one preferred to the other. All you need to do when you are confronted with this kind of research or output is to ask the person or make it absolutely clear just exactly which definition they are using, because I have actually seen both, okay? Is everyone okay with that? So some people would regard a kurtosis of 3 to mean that there is no kurtosis problem, because they don't count, not that they don't count, they in their calculation they discard this part. So if you forget about this constant at the end, yes, 3 would mean no kurtosis. Yes, correct. Okay, but if you include that number, then the reading that you are looking for then would be 0. Okay, everyone is okay. All right. I'm going to show you the answers here. Now, so what you have is these are stock returns. You can see that regardless of whether you look at it from 1926 for practically 80 years, or when you look at this period, or when you look at this now 1926 to 1941, if you know a little bit about history, not just but history in finance particularly, So that is what we call the prohibition or the depression era, when there was a crash in 1929, and then for the next 10 years, the world was quite miserable in the United States and in Europe, which led to the rise of Hitler and World War II and so on. Um, Regardless of what you do, you can see that the kurtosis here is negative. Now, negative kurtosis means the exact opposite of what I'm showing you here. So negative kurtosis, if I may draw in red, perhaps. So negative kurtosis will be thinner tails, and then the bulging in the middle, and then the peak is lower. Now I know it's not pretty. Okay, I try my best. So this would be negative kurtosis. Now I am a little bit surprised that when you look at the output, assuming the answer is correct, I'm a little bit surprised that in the long run there is negative kurtosis in the market. But then I thought about this a little bit more, and I have to say, because notice in the question, they are using uh, uh, annual data. Okay, so 1 year HPR. So what that means is they are looking at numbers, only once a year. Oh, sorry, that was not the right question. So here, annual data. Now, I think this, for me, is I have some reservations on that, because what it means is over a period of time. So let's say you look at it at the end of year 1 or 2 or 3, 4, 5, and so on, and just every year you just take a look at, one number at the end of the year, let's say on December 31st, and then you just analyze based on that, and then you come out with a kurtosis reading. Now, the problem with doing this is you would then be ignoring all of the action that is happening in between. So the market might be doing this, yes. It might be doing this. You would not be able to capture it because you're not analyzing that data. And my point to you is that if you look at all the literature regarding financial market returns, and I mean at least monthly returns, maybe even daily returns, you ask any trader, they would likely tell you that the market has some degree of positive kurtosis. Now, what does that even mean when the market has positive kurtosis? I'll tell you what it means. I'll switch back to blue. It means two things: that the market either stays in a narrow range more often than you would expect. How much more? By the size of this area here. So the market either stays in a very narrow range. The market is either really, really boring and going nowhere, or it becomes extremely volatile more often than we might expect. Now, I think that is typically what we have been seeing in the behavior of contemporary financial markets. So either they don't really move, or when they move, boy, they move like a roller coaster. And you get some really extreme up shocks and down shocks. You know what I'm saying? And this actually has relevance also to option pricing, which you guys will learn, I think, next term. You hear all the time people talk about the volatility skews. I think it's actually volatility kurtosis, but they talk about what do they mean by that when option traders do not price options according to a normal distribution, because they think a normal distribution does not capture the true probability of a market crash. What is it missing? It is missing exactly this part here. Okay, so they want to make some adjustments. So that alone, I think, tells you that the market suffers from potential fat tails, or technically positive kurtosis. Okay, is everyone okay with that? Now, so what we've done today actually is I wanted to relate these concepts to you on how to interpret data in a normal distribution, the first, second, third, and fourth moment. So mean, standard deviation, skewness, kurtosis, how it relates to real markets, in my view, and why it is relevant. And before that, we had a look at the regression, and do not confuse, the coefficient, the correlation with the regression coefficient that you get, when you get an equation like this. Okay, this is not the correlation. Okay. And before that, we also had a look at prospect theory, and how I think it explains human nature at various points when you are making a lot of money, or when you have a bit of money in your pocket and you become risk averse. But when you are losing a lot of money, how do you behave? Or when you are losing a little bit of money, how? Actually, it's 4 different psychological reactions that we can keep in mind. Okay, and then for just for housekeeping, so like I said, so there will be 2 teams presenting next week, and who are they again? I wrote that down just now. Okay, I'll just remind you. So it will be Alpha chose us. Indeed, we chose you tonight. And also Fortune Teller. Okay, so I want to thank everybody for doing their work so diligently. And I also thank you again, sincerely, for your understanding and for your patience in these very difficult times. I really do appreciate it. And if you want to do some exercise for this week's homework, so that is, so next week we'll go through these ones, okay, which I already I prepared the answers, and I'm happy to go through it with you. But next week, if you feel like doing some homework, it will be chapters 8 and 9, problem 17, 18, and chapter 9, problem 9 and 20. Okay. If you're too busy, don't worry, but obviously it's good for you if you do get around to doing it. Does anyone want to ask me any questions? Feel free to do so. Anyone? Is everyone hungry, or have you? I hope you guys have had dinner. Any questions from anybody? Okay, I have a question. So, uh, did some of you have a class today? So that would be 6592, correct? 10 a.m. You advanced financial management. I thought some of you had a class in the afternoon, no? So that is from, am I right to say that is from 1:30 to 4:30? So that is a regular event, right? And that is held in CYT 410. I'm looking at the timetable now. Okay, so all of you had a class today, or only some? Did anyone manage to stay home and didn't go anywhere today? Nobody. So everyone had a class. Okay. I'm just trying to see how if we were to move the Thursday evening tutorial, I'm going to move that somewhere. I'm just trying to figure out where. But okay. Uh, yes, sure, correct. Uh, you know, it's like a balloon. So when you are squeezing, okay, this is getting confusing. So if this is the normal distribution, back. Was that a Zishan speaking just now? Okay. If you have a normal distribution, uh, so it's kind of like a balloon, and imagine you are squeezing. If you apply pressure to these two sides, okay. Imagine this, I know it doesn't look like a balloon, but some kind of a jelly, and you apply pressure here and here. If it's jelly or there's water inside, you apply pressure here, then what will happen is it's going to cave in, and then the air will go somewhere else. Because don't forget that no matter what you do, no matter what you do, the area underneath has to add up to 1 or 100%. So that part doesn't change. Okay, that's the whole idea of probability distributions. It is supposed to characterize the chance of something happening at a certain point. So if you keep squeezing it, then the distribution will change shape into something like this. Then you get a higher peak and fatter tails. Okay. So in other words, it becomes thin around the belly, if you can call it that, and then the irregularities, they exhibit themselves around the peak area and the tail area. Okay. Okay. Yeah, you're welcome. Anybody else? Yeah. The blue area. Which blue area? Uh, yeah, I'm trying to figure out what is a good way. Or I know what you are thinking. Um, a a more straightforward way to put this might be to say that uh, if a distribution has positive kurtosis, then the chance of extreme events is higher than what you would normally expect. So in a way, you are right, because if you think about a normal distribution, so let's say the chance that the so let's say this is minus 20%. So the chance of it having a crash, according to the normal distribution, may be this area. So this area might be, well, God knows. Okay, so maybe it has a 4% chance. Okay, but in the event that your distribution actually has, some degree of kurtosis, then you are right. In that case, the chance that the market can crash more than 20% is not only this area, but but this part, all of that, all of it, including the upper part. That's the key point. So that could be like 6%, let's say. So yes, it is in a way it is more risky. It depends what you mean by more risky. Risk, uh, the common understanding, people, fund managers or risk managers, the way they understand risk is the I guess the degree of dispersion and also the chance of it happening. So in that regard, I think you are right. Yes, it is more risky. It is more risky. Yeah. Thank you. That's a good question. That. Yeah. You're welcome. Yeah. So in other words, financial markets are riskier than the normal distribution would suggest, and that is precisely what option traders are trying to compensate for when they are pricing puts or calls. Okay. All right. It is now 8 o'clock, and I hope it has been helpful. And I look forward to seeing you guys tomorrow. So although it's a bit challenging to have a tutorial like this, we do still meet in Rio. We will do that in just a little over 12 hours. Okay. I wish you a very good evening. And the last thing is, please have a look at the tutorial file number 5. And like I said, there should be a link where here, okay? So you click on that link, please, and go in there and you can update those prices, please. All right? Everyone is okay with that? Okay, I thank you once again not coming, for attending this tutorial, and I wish you a very good evening. Okay, and I will put a video copy of this online for anyone who wants to review it. Okay, thank you, everyone. Have a nice evening. Okay. Good night. You're welcome. You're welcome.